Today we're going to talk about counting sample points. Now, you see counting and you probably think that it's going to be a super easy thing to do, and sometimes it really is. But counting can get super complicated very quickly, and we're going to get into some of the nuances of it today. So if it starts out feeling boring, don't just stop and quit watching and quit working on it, all right? It's going to get more challenging, so hang with it, keep working on it, work some problems. They're all a little bit different, and you'll be all right. The underlying principle that we'll be using when we're counting sample points is the fundamental principle of counting. This is more commonly referred to as the multiplication rule. What this rule says is if an operation can be performed in n sub 1 ways, and if for each of those ways a second operation can be performed in n sub 2 ways, then the two operations can be performed together in n sub 1 times n sub 2 ways. So we're going to take a look at an example that'll show us how this plays out. So we're going to roll a die, and then flip a coin. So when I roll a die, I have 6 possible outcomes, namely 1, 2, 3, 4, 5, or 6. And if I flip a coin after that, for each number that I could have gotten on the die, I can get heads or tails flipping the coin. So I can make a tree diagram, like I've been doing here, where I show all the possible sample points that I can end up with by having numbers branching off to the various coin flip options. And if you look at that, what I end up with, each one of these red lines that I'm making, is a possible outcome. It's one of our sample points. So if you look at this initial part, I had 6 possible outcomes. And then for each of those outcomes, there were 2 outcomes possible. And if I look at how many sample points I have, I really have 2 plus 2 plus 2 plus 2 plus 2 plus 2. And I'm actually adding 2 to itself 6 times, which is the very definition of multiplication. So what the multiplication rule allows me to do is, instead of having to make a tree diagram and notice that I'm doing this repeated addition over and over again, I can instead say, here's n sub 1, that was 6 ways, and then here's n sub 2, I had 2 ways. And so the multiplication rule says the number of sample points equals n sub 1 times n sub 2, which in my case equals 6 times 2, or 12. Now, if you need to list out what all of the sample points are, you still need to make some kind of tree so that you can see what the possibilities are. And you could go through and say, this is 1 heads, this is 1 tails, and so on down, and make a list, make your sample, and make a list of your sample points to make the sample space set. But if you just need to know the number of sample points, which is very common that we need to know that number, then we can use this multiplication rule. A more common version of this rule that you'll be using, because you usually have more than 2 operations being performed, is the generalized multiplication rule. So what this says is, if an operation can be performed in n sub 1 ways, and if for each of those a second operation can be performed in n sub 2 ways, And for each of the first two, a third operation can be performed in n sub 3 ways, and so forth. Then the sequence of k operations can be performed in n sub 1 times n sub 2, all the way up to multiplying by n sub k ways. So if we think about making a tree diagram of this, say I started out with I can have heads or tails, and then I could choose that I'm randomly choosing a number 1 through 3. And then the next time I'm flipping another coin, so I've got heads or tails options. And I could keep on going with this, but we'll stop at 3. So if we look at, and I want to know how many branches I have, well, I had 2 possible outcomes. Then I had 3 possible outcomes, so I was adding 3 to itself twice, so multiplying 2 times 3. And then for each one of those 6 possibilities, I had 2 outcomes. And so I was really adding 2 to itself 6 times. So I could do 2 times 3 times 2 and find that I have 12 possible sample points. One of the places where we see the multiplication rule be very helpful to us is when we're dealing with generating passwords or names or license plate numbers or anything where we have letters involved and numbers involved. If you think about it, every time we have an operation where we're choosing a letter, we have 26 branches that we're putting into any kind of outcome tree. If we use a number, we have 10 every time. So that's big numbers of branches to draw, and your paper will very quickly become way too small. So the multiplication rule is super helpful to us. So say we want to generate a password that has 5 characters that follows the pattern letter, letter, number, number, number. And the first time that we do this, we're going to allow the letters to repeat themselves and the numbers to repeat themselves. So whenever I'm working on a problem like this, I look and I say, all right, how many spaces am I trying to fill? So I'm trying to fill 5 spaces. So I actually draw the 5 spaces that I'm trying to fill. And then if I know something about the spaces, sometimes I'll write that in the space. So I know this is going to be a letter. I know this is going to be a letter. I know this is a number. This is a number. And this is a number. So what I've done is I've lined this up and I've generated my password without putting in any specific operation and any specific options. So then what I do is I look at what was in the blank and I say, all right, how many possibilities do I have for that? So I can have a letter here, and my letter is going to be one of the English alphabet letters. So how many are there? Well, there are 26. And then again, I have another letter, and I'm allowed to repeat letters, so I still have 26 possible letters. And then I think about how many numbers I have. Well, I can have 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So there are actually 10 numbers that I can have. And again, I can have repetition, so it doesn't matter what my first number was, I can still have 10 numbers. And then I can have 10 numbers in my last blank. So now what I've done by putting the numbers below my blanks is I can go through and I can multiply in between each one of these. And I can find out how many passwords I have in this way. So when I multiply, I find that I have 676,000 possible passwords. So that makes a password this way fairly secure. If it's decently random, something would have to go through and check that many passwords. And so a human being's definitely not going to do that. Now let's take a look at what happens if we don't allow repetition. So I would do the same exact thing. So I would draw my 5 lines, and on each of them I'd write what I know. So my first one is going to be a letter. The second one is going to be a different letter. My third one is going to be a number, which is guaranteed to be different than my letters. My fourth one will be a different number. And my fifth one will be yet another different number. And then I go through and I think the same thing. So how many letters do I have to choose from? I have 26. And then if I have to have a different letter, well, I have the 26 letters, except I have one less because I've already used one of them as my first letter. So there's actually 25 remaining letters that I can choose from. Then when I go to choose my first number, I have the numbers 0 through 9 again to choose, so I have 10 numbers. With the number having to be different for my fourth option, I have the 10 numbers, but I've already used one of them, so I only have 9 remaining options. And then for the fifth one, I have to have a different number yet, so I've already used 2 of my possible 10 numbers, and so there are only 8 remaining possible numbers. So again, once I've got all of my numbers filled in of the possible outcomes, I take and I multiply them together. And once I've multiplied them together, I find that I have 468,000 possible passwords that way. So notice just by not allowing repetition, I've decreased the number of passwords that I have by over 200,000. So these numbers really do add up very quickly. Stepping up our difficulty of counting a little bit, we have a thing called a permutation. A permutation is an arrangement of all or part of a set of objects. So when we do this, the order matters. So we're talking about the arrangement, and we care what comes first, what comes second, and what comes third. So this is very similar to the password example we were giving, except for we have a set of objects we're working with. So here I'm going to work with the set of objects 2, 4, and 6. And I'm going to list all the possible arrangements of all 3 sets of objects. So I could have 2, 4, and 6. I could have 2, 6, and 4. I could have 4, 2, and 6. I could have 4, 6, and 2. I have 6, 2, and 4. And I could have 6, 4, and 2. Now, all 3 of those consist of the same objects, but they're in a different order. And with a permutation, we care about the order. And so we have 6 different possibilities there. Now, notice it says, or part of a set of objects. So we also could have 2 and 4, 2 and 6, 4 and 2, 4 and 6, 6 and 2, or 6 and 4 as possibilities that are permutations of this set. So they're arrangements of part of this set of objects. And similarly, we could have 2, 4, or 6. Normally, when we talk about a permutation, we want to focus on we'll be focusing on ones where we're saying, hey, you have this set of objects and we know we want a 3 permutation or a permutation of length 3. So we'll know how many objects are going to be in our permutation, so we won't have to consider all of the possible decreasing number of objects that could be in our permutation. So if we were to try and count how many ways we could do this, how many permutations there are of a set of 3 objects, then we basically are looking at having 3 blanks that we're filling in. And I know that they're from my set, say S here. So this is S, and this is a different element in S. And this is yet another different element in my set S. All right. So if I think about how many there are, well, I have 3. And then a different one, there's only 2 left. And a different one, there's only 1 left. And so I multiply those together, and I get 6 possible outcomes, 6 possible sample points here in my permutation, or 6 possible permutations. And I get 6 possible permutations. So this is going to be a thing that happens a lot where we're using the entire set, and so we end up multiplying the number of elements in the set times 1 less, until we get down to 1. And when we do that, what we're doing is we're actually doing a thing called a factorial. So we could write this as 3 with an exclamation point. And whenever you see that, what this is telling you to do is 3 times 2 times 1. So generalizing that, we have n factorial which we write as n exclamation point, tells me to do n times n minus 1 times n minus 2. And to keep multiplying that, now I get down to 2 and then 1. And that is a way that we use some shorthand so that we don't have to write out all of these different possibilities sometimes. And we don't have to write out this whole multiplication problem. We can just write out the shorthand. So really quick, one special case is sometimes we end up thinking about 0 factorial. And 0 is already below 1, so it doesn't really make a ton of sense for us. Whenever we see a 0 factorial, that is equal to 1. So it's no mistake that factorials came up right after we talked about permutations, because we actually have our first theorem here of our course, that the number of permutations of n objects is n factorial. So we can actually use factorials to help us when we're counting permutations. So sometimes we want to take permutations of not the entire set of objects. We only want a couple of objects from a possibility of more. And we actually saw that in our password example, where we wanted 2 letters from the possible 26 letters. So we've actually already seen this play out a little bit. So say we wanted permutations of 2 objects from a set of 4. Well, what we do is, again, our multiplication rule. I have 4 possible objects. I have my whole set, and then I have a different element from the set. So I have 4 possibilities for my first element and 3 possibilities for my second element. I multiply them together, and I find that I have 12 possibilities. So we can do this with any number, any size set to start with, and any number of elements from that set. And we can actually use what this ends up being is this is the number of elements in the set, and this is 1 less, which also happens to equal, in our case, the number of elements in the set minus the number of elements we're choosing from the set plus 1. So this was 4. This was 4 minus 1, which is going to equal 4 minus the 2 that we were choosing to be in our permutation plus 1. And if you notice, this side is 3, and this side is also 3. So we have a multiplication that's happening here that's actually n times n minus 1 times n minus 2, and so on until we get down to n minus r plus 1. And that's what our number of permutations. So this is number of permutations of size r. So size r from a set of n objects. So this is permutation size. All right, and we use this lowercase n in front of a p with a subscript r after it, and it's always in this order. So the set of n objects is the thing that's out in front of the p. The p is telling us we're taking permutations, and that subscript r is telling us how many objects are going to be in our permutation. And this equation right here, this is going back to our multiplication rule. It's not ideal, and we have these things, these factorials that we've developed to be able to use, so we want to be able to use them. So we actually have NPR. Can remember it, right? The order, NPR, radio station. All right, this is n factorial divided by n minus r factorial. So you see, everything after n minus r has been cut off of this factorial. And so it's the same as dividing by it, canceling all of them out. And that brings us to our next theorem. So this theorem is that the number of permutations of n distinct objects taken r at a time is NPR equals n factorial over n minus r factorial. So note n distinct objects, that's the number of elements in our set, and when we say that they're taken r at a time, that's the size of our permutation. So an example of this playing out, say we're going to try and make a password again. This time it has to have 4 numbers. Now, it's important to note that permutations have no repetition. So if our password is supposed to allow repetition, permutations won't work for us. So we're going to say we have no repetition allowed so that we can use our permutations. So no repetition. So in this, I know I have my giant P, and I'm taking a permutation of n distinct objects. So I think about it and I say, how many numbers do I have? Okay, there are 10 distinct numbers. And then I look at it and I say, I'm taking r at a time. How many numbers do I need? I need 4. So this is a permutation of size 4 from a set of 10 objects. And I plug these numbers in then. So n was 10, so I have 10 factorial. And I'm going to divide that by, again, n was 10, so I'll plug in 10. And r was 4, so I'll plug in 4 factorial. And if I combine the things in my parentheses following my order of operations, I have 10 factorial divided by 6 factorial. Now, when you're thinking about order of operations, factorials are multiplication. So you should be thinking about them as multiplication. So these numbers can get fairly big fairly quickly. Factorials grow really fast. So one of the things that we do sometimes is we do some of the work for our calculator before putting these things into our calculator. So you can look at this. This is actually 10 times 9 times 8 times 7 times 6 all the way down to 1. And in my denominator, I have 6 times 5 all the way down to 1. And if I look at it, my numerator and denominator both have a 6. They'll both have a 5, a 4, a 3, a 2, a 1, 4, right? So we have everything canceling out except for this magic part right here, which is really going back to our multiplication rule. So you can either do that work ahead of time for your calculator, and if your calculator seems to be crashing when it's trying to do the factorials that you're asking it to do, then this is definitely the way you want to go. If it seems to be handling them okay, then you can absolutely do that. Your calculator will have a factorial button on it. It'll have an exclamation point there available to you. So it's just a matter of finding that exclamation point. Sometimes it's some second option. So we'll write this out both ways. So 10 factorial is 3,628,800. And 6 factorial is 720. So you just see that growth from between 6 and 7 or 6 and 10, how much it grew. It's just huge. And if you do that division, you'll get 3,628,800 divided by 720, which is 5,040. And I'm putting this here because if we do our other option of 10 times 9 times 8 times 7, doing the multiplication rule, you'll get 5,040 as your answer. So notice all of the permutations we've done so far have been in lines. They've been some kind of password or something like that. Sometimes we are actually dealing with what are called circular permutations. You can think about this as people sitting around a table. So if I set the numbers 1, 2, 3, 4, 5, and 6 around the table, now it doesn't matter where I start reading these. So in this case, a permutation that I would read as 2, 3, 5, 6, 1 is actually the same as a permutation that I would read as 6, 1, 2, 3, 4, 5. So when it looks like, when we put the numbers around a circle, if they look like they're in the same order around the circle, regardless of where we start and stop our reading, we don't want those to be different permutations. We want to see this as the same table setting. So when we do this, what we do is we take one person and we say, all right, person number 6, they are going to be at this location. We're always going to start with number 6 in reading these. So regardless of where number 6 is, that'll be our first entry. And then we'll read clockwise from there. So when we think about it that way, then it becomes really clear that when we're talking about circular permutations, it becomes really clear that when we're talking about circular permutations, we want to think about all of the remaining people other than our fixed person that we're always going to start with. And so if I look at that, if I want to seat n people, so seating n people, one of the people is fixed. So 1's fixed. That's my starting point. And then I get to choose seats for the remaining 5 people. So I choose seats for the remaining n minus 1 people. So that makes it clear to us, hopefully, that the number of permutations of n objects arranged in a circle is n minus 1 factorial. And this is actually a theorem for us as well. Sometimes when we're looking at permutations, we have a little bit less distinction than being able to say that things are unique letters or numbers or something like that. And so we do have a way of dealing with that. So here's an example of how that might play out or what it might look like for us. So say I'm trying to take a class that I have 10 people in. All right, so 10 students. And I have 6 engineering majors, 3 education majors, and 1 math major. And I want to call on these students in a random order. I'm just going to call them out. And the only thing that I really care about, though, is what their major is. So I want to know, like, how many different orders I can call them out in when all I really see about these students is their majors. So when I do this, when you think about it, I can have the 10 students, I can put them in 10 factorial orders, right? I can put them in any of the 10 factorial orders, but there's going to be people who kind of get grouped together for me. So if I have like an engineer, I'm going to use lowercase e for education. All right, so engineer, education, math, engineer, education, engineer. All right, so I can interchange my engineers in any possible way, and I can't tell the difference. All right, so what we do is we divide out by all the possible orders that the engineers could end up in. So I have 6 engineers, so the permutations of my engineers, I have 6 of them. And then the education majors could also be playing games, flip-flopping around any way that they want. And so I also look at them and I say, all right, there's 3 of them, so the permutations that the engineer or the education majors could have, well, that's 3 factorial ways that they could rearrange. And then I look at the math major and I go, oh, nope, the math major, I can tell who the math major is. There's only 1 of them. So I would be dividing out by the 1 factorial for the 1 math major. All right. And so when I do that, what I'm effectively doing is I'm canceling out some of my where students, if I was distinguishing by name, say, would be in different orders, but since I'm only looking at majors, I'm actually seeing all the same. So when I do this multiplication and division, I end up finding that I have 840 possible orders that I could call on my students. And that's a whole lot less than the 10 factorial if I was distinguishing by names. So when you distinguish, you take things and you have less distinction between them, you greatly reduce the number of possible permutations you have. And this is, again, another theorem for us. So the number of distinct permutations of n things, of which n1 are of one kind and 2 are of a second kind, so on, n sub k are of a kth kind is, we take n factorial divided by n sub 1 factorial, n sub 2 factorial, times all the way up to n sub k factorial. Here's another type of counting problem that comes up a decent amount. So say I have 9 students and I want to put them into 3 groups. One of them is going to be a pair, one of them a group of 3, and one of them a group of 4. What this is doing basically is what we call partitioning a set into some subsets or cells. So I'm going to partition my 9 students into 3 cells. Now, when I'm doing this, I clearly don't want any of my students to be in more than one of my groups. And that's whenever we talk about partitions. So each element is in exactly one cell. And I don't really care what order the cells are in. So I don't really care if the pair comes first or the next. It doesn't matter at all to me. So what I'm essentially doing here is I have my 9 students, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And what I want to know is how many ways can I take a pair of them, and then 3 of them, and then 4 of them. Well, that's one way I could do it. I also could take a pair, and then 3, and then 4. And I also could do things more complicated, right, for the way I've got them written. So that could be my pair. This could be my group of 4, or 3, sorry. And then this could be my group of 4. So there's multiple ways that I can do this. So one way that we can think about how we're going to do this. So one way I can think about doing this actually is to take my 9 elements in my set and say I'm going to put them in some order. And I can put them in any order. So I have 9 factorial ways of doing that. Now once I've put those 9 elements in an order, I'm going to always take my pair, and then my group of 3, and then my group of 4. And because I've put the 9 elements in every possible order, I've also now grouped my pair, my group of 3, and my group of 4 in every possible way. The thing is, though, I don't actually care who was the first person in the pair and who's the second person. They're a pair. They're working together as a pair. So when I do this, I actually have to divide out by the possible orders within. So in my pair, there are 2 factorial ways that those 2 numbers could fall out. In my triple, in my group of 3, I could have 3 factorial orders that those people could fall into. And I don't care because they're all a group of 3 and I see them as a group. And the same thing with the group of 4. Now it's a group of 4 and they're in any order. They're all a group of 4 and that's what I really care about. So I divide out by all of those. And when I do that division and all of those factorials, I get 1,260 ways that I could put my class into a pair, a group of 3, and a group of 4. So we can yet again generalize this example that we just worked out, where we're putting things into cells, and we get another theorem in doing so. So the number of ways to partition a set of n objects into R cells with n sub 1 elements in the first cell n sub 2 elements in the second cell, and so forth, is, and we get our equation that we used up there. So we have n factorial divided by n sub 1 factorial, n sub 2 factorial, and so forth until we get to n sub r factorial. And now we also have this special notation where we're actually saying we have n elements and we're going to choose from them n sub 1, and then we'll choose n sub 2 elements, and so on until we're choosing n sub r elements. And we separate those with commas. And we said when we were doing a partition, everything had to be in exactly one of our cells. So every element in exactly one of our cells numbered 1 through r. So we also have to have, for this theorem, n1 plus n2. And if we add them all up to nr, this is going to actually equal n. So that's our theorem right there. So through all of this, we've been worried about order. Permutations always are caring about order. But notice when we were talking about this partition thing, within the groups of 2, 3, and 4 of my students, I didn't care what order they were in within those groups. So when we're doing partitions, we actually have a way of selecting elements without caring about the order. So say I want to pick 3 people from 10 to serve on a board. All right, so the board doesn't have any kind of distinguished positions that any of these people can have, so I don't really care what order they get selected in. All I care is that 3 people get selected. So when I do this, I can go through and I'm basically taking my 10 people, putting them in any order I want. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can put them in any order I want, so I have 10 factorial possibilities. And then I'm choosing 3 for the board. So if I can put them in any order, I can say that the first 3 are always on my board. And I've essentially partitioned them into people on the board and people not. All right? So I can take my 10 factorial and I can divide it by the 3 people that are on, being any order that they want to be in, so the orders that could happen, and then the 7 people who are not, all of the orders that they could be in. And when I divide that out, then what I've done is I've chosen my board, I've chosen 3 people from a group of 10 where order doesn't matter at all. And when I do that work, I get 120 possible ways to choose 3 people from my group of 10 to serve on the board. Now again, we can generalize this. So notice I have n factorial in my numerator. I have r factorial in my denominator. And my other number, the other size of my partition, was really n minus r. And I took the factorial. So 10 minus 3 gave me 7. So when I do this, what I've essentially done is I've made a partition from 10 objects into R and n minus R. So when we're doing this, because we always know R and n minus R, that n minus R depends on R, we actually write this as just n choose R. So we know we're choosing R of them, and we know that n minus R are not getting chosen. This is called a combination. So in permutations, we care about the order. In combinations, we do not. And of course, it wouldn't be complete if we didn't have a quick theorem about combinations to close out our section. So the number of combinations of n distinct objects taken R at a time is n choose R equals n factorial divided by R factorial times n minus R factorial. So again, permutations, order matters. Combinations, order does not. Permutations, order matters. Combinations, order does not matter. Permutations, order matters. Combinations, order does not matter. I cannot repeat that enough times. Please take the time to drill that into your brain.